Okay, in our last chapter we looked at momentum, and we learned that we had what we call the conservation of momentum. So what's it mean when something is conserved? Remember that term?
It's kept.
It's what?
Like it's kept. Like it stays.
Oh, okay, yeah. It stays. It has a set amount. So conservation means that it's not created or destroyed. So when we set our momentum equations equal to one another, right, before momentum equals after momentum, that means that we had a true conservation of momentum. So that's what we're looking at here in terms of energy as well. So energy within the system will always be conserved. And we're going to talk about a couple different types of energy, but we're going to look at the conservation of energy in this chapter. So we already looked at the conservation of momentum in chapter 9. Now we're going to look at the conservation of energy in chapter 10 and 11. Okay? So today we're going to start by talking about this concept of work. And doing work in physics is different than what we think the generic term work means, right? Physics work is different than, other types of work. Okay, so work has a long definition. But what I want you to think about work being is displacement times the force, okay, or force over a certain amount of displacement. Oops. So here is your equation down here at the bottom for work. Work equals force times displacement. And in this definition, there's something that hopefully sticks out to you, or at least looks a little bit different, when it says the force parallel to the displacement. So that means if we apply a force that's not parallel to our displacement, we have to break down that force to find the parallel component of our displacement. So we want to make sure that when we're solving our work, our force applied and our displacement have to be in at least the same plane, right? They need to be parallel to one another. So we'll talk about what that means here in just a second. But force times displacement, and sometimes if you want to label it force parallel, you can do that. You don't have to. Some textbooks label it like that, but all that means, this just means that the force has to be parallel to the displacement. Okay, so when we're looking at work, we have to think about specifically what force is running the same direction as our displacement, whether our displacement is horizontal or vertical. Okay, so parallel is the component of our force. So if you just look at this case right here, you don't have to necessarily write this part down. But if you look at this example, we're applying a force upward at an angle. Right, we're pulling upward on this box at an angle. But the displacement is going what direction? Purely what? Yeah, east or horizontal, right? The displacement is moving horizontal, so you're dragging this box. But we're applying an upward force at an angle, which means those two things are not parallel to each other. So if we just looked at this force, right, that's our applied force and our displacement, are they parallel to one another? No. So what we have to do is we have to find the parallel component of that force. So we would take our angle, times our times cosine, times our hypotenuse to find the parallel component of that force, right? And if our displacement was going vertical, right, if we were lifting the box, we would want to find the vertical component of that force, right? Whatever things make this run parallel to each other, that's the force that we need to be using. Does that kind of make sense? So you can put this equation down if you want. Cosine won't always be the case though. So you have to really make sure that you're reading where your force is being applied and where your displacement's going to be. Okay, so you're welcome to write this equation down, but I want you to understand that maybe it's not always cosine, okay? Just something you need to think about there. Okay, let's try this. If you pushed a grocery cart a distance of 50 meters by exerting a horizontal force of 30 newtons on the cart, how much work would be done? the unit would just be newtons times meters, because it's just force times displacement. Right? Is our displacement on our cart horizontal or vertical? Horizontal, right? We're pushing the cart, so it's not being lifted. It's not leaving the ground, right? Our displacement is purely horizontal, and it says that our force is purely horizontal. So to find our work, all we really have to do is force times displacement. That's it. Okay, so since we had simple forces and simple displacements here, it made our problem really easy. Okay, and for right now, our unit is Newton times meters. Right, we're actually going to get a new unit here in just a second, but for right now, newtons times meters. Okay, questions here? Right, they do get a little more complex than that, but not too bad. Okay, the unit for work, instead of being a newton meter, is called a joule. Okay, so 1 newton meter is equal to 1 joule. Has anyone heard the term joule before? Maybe? Okay, in college chemistry, you'll start dealing with kilojoules of energy and things like that. But joule is an energy and a work unit. So joule is just given by a capital J. Okay, so think about these, discuss these with the person next to you, okay, or close in proximity to you, and see if we can come up with an answer. You have to pay attention to if you're looking at work done on an object or work done by an object. Sometimes they're the same value, sometimes they're not. So in this case, right, I was doing work on the book when I lifted it, or this box when I lifted it, right? The same amount of work was being done on the box, right? Those two things should be the same number. Those aren't always the case, but we need to look at whether we're done on an object or by an object. And then we also need to look at if we're looking at specifically work done by friction, or work done by the applied force, or work done by the whole system, which would be called net work. Okay? So if I'm looking at just specifically work done by friction, what force would I be dealing with? The frictional force, right? That's it. If I'm looking at just work done by gravity, what force am I looking at? The gravitational force, right? So we have to think about, are we looking at work done by a specific type of force, or are we looking at the net work of our system? Okay? Those are two different things. All right, let's try this one here. A 50-kilogram crate is pulled 40 meters along a horizontal floor by a constant force of 100 newtons at 37 degrees. The floor exerts a frictional force. Determine the work done on the crate. So in this case, we want the total amount of work, right? The net work. So I'll give you a couple seconds to get this written down, and then we will start looking at it together. All right, so it tells me my displacement is 40 meters. Oops. It tells me my applied force is 100 newtons at 37 degrees. Okay, it also tells us that we have a frictional force of 50 newtons. So where does our frictional force need to go? On the right or on the left? On the left, right? It's got to oppose our motion. So if our displacement is purely horizontal, what component of this force are we going to be concerned with? The vertical or the horizontal? The horizontal. I need to find the horizontal force, right? What's the horizontal component of that force? So I'm going to break it down. Okay, we have that triangle, our force triangle. We're going to break it down using sine, cosine, or tangent, right? In this case, we're going to use cosine. So the x component of that force, we would find by taking 100 times cosine of 37. Are we on the same page with why we're doing that? Okay. So that gives us about 79.9 newtons. So that's the x component of our applied force. Okay, and so we want to find the net work on our system. So I think the simplest way to do that rather than to solve for work done by the applied force and work done by the frictional force and then subtract, is to just find your net force first. So our net force in the horizontal direction would be positive forces, 79.9, minus negative forces. Right? Does that make sense? Do you remember that part of our forces chapter? Yeah, the net force, we're trying to solve for the net work, which is overall. So I want to find the overall horizontal force first. So the way I do that is I take positive forces, because it's going to the right, minus my negative force. Okay? So my net force would be 79.9 minus 50, which gives me a net horizontal force of positive 29.9. So now when I go to solve for work, I'm going to take force times displacement, and I'm going to use this net force right here. And my displacement was 40 meters. This next problem, so we're going to find the work done by a hiker to lift the backpack up our hill. And we're going to break this down and kind of solve it step by step with this particular one. Determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill, a height of 10 meters at constant velocity. So I gave you a little diagram here of what this looks like. But it's really important here that it says we just want to find the work done by the hiker. Just the work done by the hiker, so not the overall system. We're just looking at how much work he is doing, and then pretty soon we'll take into account gravity, and then we'll look at the whole system. But for right now, it's just the work done by the hiker. So here's my free body diagram right here. The force that the hiker is applying on that backpack is in what direction? Right, north or vertical, right? Purely vertical, because on that hiker, that backpack is sitting on his back, so he's just applying enough force to keep it off the ground, right? He's just holding it up. He's overcoming gravity. So his force is purely vertical. So the displacement that we care about is purely vertical. We don't care how he gets up the hill, right? We don't even care if he takes the escalator up the hill, right? We care about how far he's ending up above where he started. So that vertical height right here is all that we care about. We don't care about the way he gets up the hill. We don't care about the actual number of steps he took, right? We care about the parallel component. So since his force is purely vertical, we only care about the vertical height that that object had to change on. Does that make sense? Okay, so to find the work done by the hiker, we would say work is equal to force times displacement. We know our displacement here is 10 meters. How do we find the force that he's applying right here? Right, on his back sits this backpack, right? So it's not accelerating on his back, which means the force of the hiker and the force of gravity should be equal to each other. Right? Does that make sense? The backpack resting on his back, he's just doing enough to overcome gravity. So the force he's applying to keep that backpack upright is just enough to overcome gravity, which means that the force done by the hiker is equal to mass times gravity. Okay, which gives me a force of 147. Okay, so he is doing 1,470 joules worth of work as he climbs up this hill, right? Enough to keep the backpack off the ground and enough to climb 10 meters. Doesn't matter if he took the escalator up to the top, right? He still technically did 1,470 joules worth of work, okay? Because he ended up 10 meters above where he started. Okay, questions there? Now we're going to look at the work done by by gravity. Okay, what's the work done by gravity on our backpack now? Right, we found the work that he was doing to lift it. Now we're going to find what's the work done by gravity in this case. Okay, you're going to find that it's an extremely similar problem. Okay? What do we know the force due to gravity here is equal to? Yeah, we know it's 147, right? Because we just solved for that. And does gravity act on it the whole 10 meters that it's being lifted? Yes. So to find the work done by gravity, we still take 147 times 10. Right? The only thing that's different here is that work done by gravity is going in what direction? Down. Right? It's a negative. That's the only thing that's different. Right? He was doing just enough work the whole time during this climb to overcome gravity. So if I want to know the net work on our system, net work on our backpack during this time, what's our net going to be? It's going to be 0, right? We did just enough work to overcome gravity that whole time. Okay, so the net work on our backpack, we would take work done by the hiker minus work done by gravity, and we get 0 joules. Okay, there's several different types of energy, but we're going to look at 2 main types. Can anybody name any types of energy for me? Okay, yeah, heat. Yeah, kinetic. You know what kinetic energy means? Okay. Kinetic energy and potential energy are going to be the 2 types that we talk about. And kina, the root kina usually means what? You know? Like kinematics? Movement. Good. Motion. So kinetic energy is an energy of an object that's in motion. Okay, but we are going to look at kinetic and potential energy in pretty in depth here. And so kinetic energy is going to be our focus today. When we talk about the energy of an object, energy in and of itself is the ability of an object to do work. The ability of an object to do work on something. Okay, which means it has the ability to apply a force and relocate that object a certain displacement, right? That would be work being done. So energy is the ability of an object to do work. Okay, kinetic energy is transferable from one object to another. In our last chapter, we talked about collisions. And we talked about the transfer of kinetic energy, right? When one object, what happens in a perfectly elastic collision of objects with equal mass? Do you remember? Right, it transfers 100%. So if my object's at rest, this first object's going to come to rest, just like we said in that example, right? If one of our objects is at rest and the other one's in motion, they should completely switch. So that's a pure, perfect transfer of kinetic energy. Okay? And so what happens when we have a purely 100% transfer of kinetic energy is literally all of that energy is just being transferred. They're just switching places. Okay? Here's our equation for kinetic energy. Ke equals 1/2 mv squared. What do you think the m probably stands for? Mass, good, and V probably stands for velocity, good, because we have to be in motion. If we have a 0 velocity, what's that mean our kinetic energy has to be? 0, good. Okay, so this is an equation that really should go on your equation sheet. Okay, we're going to use that one a lot. Okay, this is what we call translational kinetic energy, so it means that things move simply from point A to point B. We're not dealing with spinning objects yet, and we won't deal with spinning objects. That makes a huge difference. Okay? All right, we're going to be able to connect work with the amount of kinetic energy being transferred. And so we're going to take this term or this concept of work and apply it to kinetic energy with this equation. The net work is equal to the change in kinetic energy. So what's delta always mean? Change in. And so specifically it means what minus what?
Final minus.
Good. Final minus initial. So in your textbook sometimes, or this time specifically put a 2 and a 1, right? I would put an F and an I for final and initial, right? Final kinetic energy minus initial kinetic energy gives us the change in work or our net work. Okay? Kinetic energy final minus kinetic energy initial. Okay. That's an equation, again, that should go on your equation sheet. So this allows us to connect work and kinetic energy. The equation right here only works when you're talking about net work. Not work done by friction, not work done by applied force, got to be the net work. Okay? Okay, blah, blah, blah. Okay, I don't need you to have any of these three first ones. We already talked about that. Kinetic energy is also measured in joules. Okay, so the unit still has to be joules. Joules is for both work and all types of energy. So all of this chapter 10 and 11 will be joules. Kinetic energy is scalar, which means it does not have to include a direction. When we talk about direction in this chapter, I want you to understand that kinetic energy doesn't necessarily have to have a cardinal direction, but it could still have a negative quantity, right? A negative quantity would tell us that we've got a loss in kinetic energy. So it still needs to have that negative, where usually that indicates direction for us, but kinetic energy still can be negative, right? A loss in kinetic energy would require a negative symbol for us.
Kinetic energy still needs to be parallel to, right?
Not necessarily. No, we won't deal with breaking down things really with kinetic energy. Okay. 145 gram baseball is thrown with a speed of 25 meters per second. What's its kinetic energy? So let's solve that first part. This has two parts to our question. And then how much work was done on our ball to make it reach this speed if it started from rest. So the first thing we want to do is find kinetic energy of our object when it's moving 25 meters per second.
Should we switch that into kilograms?
Exactly, good. Okay, does grams stick out to everybody? Okay, that should be a red flag for us, so we need to divide that by 1,000 to get it to kilograms. So that gives us 0.145 kilograms for our mass. So mass has to be in kilograms, velocity has to be in meters per second. So kinetic energy equals mass, 1/2 times mass times velocity squared. A lot of you will forget that squared, okay? It's really important that it's only the velocity term that's squared here. It's not the whole equation, it's just velocity that's being squared. Okay? So did we get about 45.3 joules? Yeah? Okay, any questions with that? The next part of it asks how much work was done on the ball to make it reach this speed if it started from rest. So what we want to find here is our work, right? And we know that work is equal to change in kinetic energy. So the final kinetic energy here is what?
45.3.
Yeah, 45.3, right? Because it was moving 25 meters per second at its final. So I'll take work equals 45.3 minus our initial kinetic energy, which was what? 0. So why is our initial kinetic energy 0? Started from rest. Good. And it can't have kinetic energy if it doesn't have any velocity. So started from rest, which means our work was positive 45.3 joules. Oops. Sorry. Okay. How much work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? So our initial velocity is 20. Our final velocity is 30. You can do this a couple different ways. You can solve for each individual kinetic energy and then subtract them. Or you could just use your equation work equals 1/2 mv squared minus 1/2 mv squared, right? I could just take final minus initial here and put it all into one equation, right? This is still change in kinetic energy. You're just doing it in one equation instead of 3 different ones. Okay, does that kind of make sense to everybody? Okay. This right here is still change in kinetic energy. You can just put it all into kind of one equation rather than solving for kinetic energy and solving for kinetic energy and then subtracting them. You can just put it all into one equation if you want. Right? This is final kinetic energy minus initial kinetic energy. So I'd say work equals 1/2 times m times 30 squared minus 1/2 times m times 20 squared. Right, here's my final velocity and my initial velocity. You can, combine those equations. You can factor out the 1/2 and the 1,000. You just have to be really careful that you're still squaring that velocity. So I don't like to factor that out if I don't have to. I'll just plug it all in at once. Okay, any questions here? If we were given our displacement too, we could find the force output by our car, right? We know that work is equal to change in kinetic energy, but we know that work is also equal to force times displacement. So if we have 2 equations that are set equal to the same thing, what could we do with those 2 equations? Do you remember? If you have 2 equations set equal to the same thing, what can you do? Yeah, you can set them equal to each other. So if we had a force and a displacement here, we could say force times displacement equals change in kinetic energy. Okay? I think this is an equation that you should probably have on your equation sheet as well. Okay? You'll sometimes, it might say, right, over a distance of 100 meters, what was the force applied by the car, right? So that would allow you to solve for that kind of in one equation again. So we need to recognize that since both of those things allow us to solve for net work, we can keep those things, we can set them equal to each other when needed or when necessary. Okay.